Integrating the trigonometric functions. Recall that the first derivative of sine x is cos x, the first derivative of cos x is equal to negative sine x, and the first derivative of tan x is equal to sec² x. Reversing all of this, we have these results. The integral of cos x dx is equal to sine x plus the constant of integration c. The integral of sine x dx is equal to negative cos x plus c. And the integral of sec² x dx is equal to tan x plus c. One way to help remember these results is with a diagram. Arrange sine x, cos x, negative sine x, and negative cos x in a circle as shown. The red arrows represent differentiation and the blue arrows represent integration. So starting with sine x, the first derivative of sine x is cos x, the first derivative of cos x is negative sine x, the first derivative of negative sine x is negative cos x, and the first derivative of negative cos x, we're back to sine x. Going backwards, the integral of sine x is negative cos x, the integral of negative cos x is negative sine x, the integral of negative sine x is cos x, and the integral of cos x is sine x. So we're back to the beginning again. Now the relationship between tan x and sec² x is not circular. In fact, it's linear. So starting with tan x, the first derivative of tan x is sec² x. Going backwards, the integral of sec² x is tan x. Here are some further results. The integral of cos of ax plus b dx, where a and b are constants, is equal to 1 over a times sine of ax plus b plus the constant of integration c. The integral of sine of ax plus b dx is equal to negative 1 over a times cos of ax plus b plus c. And the integral of sec² ax plus b dx is equal to 1 over a tan of ax plus b plus c. Now the integral of tan x dx may be accomplished by expressing tan x in terms of sine x and cos x. So the integral of tan x dx is equal to the integral of sine x over cos x dx. We have a reciprocal function where the numerator is some multiple of the derivative of the denominator. In fact, the derivative of cos x is negative sine x. So by changing the numerator to negative sine x, and then compensating for this by putting a negative in front of the integral, we now have the integral of tan x dx is equal to negative integral of negative sine x over cos x dx. This is now in the form of the integral f dash of x over f of x, which equals negative ln of the absolute value of cos x plus c, or it can be written as ln of absolute value of sec x plus c. Example 1. Find the area bounded by the curve y equals sine x from x equals negative pi over 2 to x equals pi over 2. Now firstly, we're finding the area bounded by the curve, which means that any negative areas or areas under the x-axis will need to be made positive or considered positive. Now it helps to draw a sketch of the curve. So here's a sketch of the curve y equals sine x from negative pi over 2 to pi over 2. And we can see that half the area is going to be positive and the other half is negative. Now it also helps to note that y equals sine x is odd. In other words, it has point symmetry about the origin. So the area under the curve from negative pi over 2 to pi over 2 can be found by integrating from 0 to pi over 2 and then doubling that area. Hence the integral from negative pi over 2 to pi over 2 of sine x dx is equal to 2 times the integral from x equals 0 to x equals pi over 2 of sine x dx. And that equals negative 2 times cos of x from x equals 0 to x equals pi over 2. And applying the limits of integration, that equals negative 2 multiplied by cos of pi over 2 minus cos of 0. And cos of pi over 2 is 0. And cos of 0 is 1. So that equals negative 2 multiplied by negative 1, which equals to 2 square units. Example 2a. Find the definite integral of cos 2x dx from x equals 0 to x equals pi over 6. Now the integral of cos 2x is half sine 2x, so the definite integral is equal to half multiplied by sine 2x from x equals 0 to x equals pi over 6. Applying the limits of integration, that equals half multiplied by sine pi over 3 minus sine of 0, which equals half sine pi over 3, which equals root 3 over 4. Now example 2b, we're going to find the indefinite integral of sine of x degrees dx. Now calculus must only be done in radians, so we need to convert x degrees into radians. And to convert degrees into radians, we divide by 180 and then multiply by pi. So this equals the indefinite integral of sine of pi over 180x dx. Now this is in the form the integral sine of ax, where a is a constant. So this equals negative cos of pi over 180x over the derivative of what's inside the brackets, so divided by pi over 180, which equals negative 180 over pi cos of x degrees. So I've converted pi over 180x back into degrees since the original question had the angle in degrees. And lastly, example 2c, find the definite integral of sec² x dx from x equals pi over 3 to x equals 2 pi over 3. Now this is undefined, since y equals sec² x has a vertical asymptote at x equals pi over 2, and pi over 2 lies between the limits of integration, and we cannot integrate across a discontinuity. So the answer here is undefined. Example 3. Find the indefinite integral of tan² x dx. Now it's relatively difficult to integrate tan² x as it is, but we can change the form of this integrand by using a Pythagorean identity. Recall that cos² x plus sin² x equals 1. Dividing all of these terms by cos² x, we get 1 plus tan² x is equal to sec² x. By making tan² x the subject of the formula, we can then form this equation. The integral of tan² x dx is equal to the integral of sec² x minus 1 dx. And we can integrate sec² x dx, that's a known result. So that equals to tan x minus x plus the constant of integration c. Example 4. Find the indefinite integral of cos x times sine to the power of 4x dx. Now the strategy is to reverse the chain rule. We can see that the integrand involves a product of two functions where one function seems to resemble the derivative of the other. In fact, if we ignore this power of 4 and just look at sine x itself, the derivative of sine x is cos x, which means that the primitive function must have involved a sine to the power of 5x. So let f of x equal sine to the power of 5x. So we're assuming that the primitive function is sine to the power of 5x. And we can write that as sine x to the power of 5. Differentiating sine x to the power of 5, we get f dash of x is equal to 5 times sine x to the power of 4 multiplied by the derivative of the inside, which is cos x. So that equals 5 cos x times sine to the power of 4x. And we can see that this expression here is a multiple of the integrand. Hence, the integral of 5 cos x sine to the power of 4x dx is equal to sine to the power of 5x. Dividing both sides of this equation by 5, we get the integral of cos x times sine to the power of 4x dx is equal to 1 over 5 times sine to the power of 5x plus the constant of integration c.